Hi, I'm Ayub. I'm CEO of D3 Companion, and today I'll walk you through the journey that we had from raw architectural drawing to clean graph structured datasets that are the base of our generative AI engine. We'll go over each step. There will be sourcing, diversification, curation, and preparing the data. Before we start, let me introduce D3 Companion. So we're a startup based in Berlin. Our main product is an AI-powered tool for AEC professionals to smooth the residential building early design phases. Our tool presents two aspects, simulation and AI. And here we're going to be focusing on the AI design workflows. So in general, here are the four-stage pipeline that will be that we have in our AI engine. So that would be dataset preparation, model training, and layout generation, and finally BIM integration. Each stage is fully automated, but has, of course, human checkpoints. In this presentation, we'll be focusing mostly on the dataset preparation, as it's one of the most technically challenging parts. Let's start with the first step, that would be data sourcing. Of course, we have the old saying, garbage in, garbage out, and that applies brutally to AI and design. We need to start by locating clean floor plans, commercial, residential, student housing, everything to guarantee representative. Where do we find the floor plans? Of course, we cannot just go to a search engine and look for floor plans. Therefore, we tap into four channels. First one would be public CAD libraries, BIM repositories, raster data that's scrapped or scanned, and fully synthetic layouts that you can get from academic datasets. It was important for us to have multiple origins so that we avoid teaching the model only one architect drafting style. Let's zoom in. So CAD gives you the geometry with layers, but no semantics. BIM offers rich object metadata. From raster, you get all the legacy blueprints, but also the public data and public floor plans. And for synthetic, you get datasets, academic datasets mostly, that allows you to go into edge cases that you rarely see in the wild. And the synthetic datasets are valuable for us because think of an L-shaped loft or some weird corners, but also they are widely available and are already pre-labeled. The trick is about the licensing, and we're going to get to that into a second. Overall, we end up with 47,000 residential units floor plan for our model, most of which are rasters. That's about 43%, with only 15% of our data sets out of BIM data, because they are the hardest to source. Step two would be the data diversity, which is more than just the sample counts. We need to diversify by region, by era, by sizes, by program, so that we prevent any geographic or style bias. As we see here, we have door swings, metric grids, and even annotation languages differ across continents. So the model must parse them all. Next step would be the data curation. And we need to curate according to multiple parameters. Of course, the resolution check, we need to check if maybe our wall is not just 1 pixel. We need to remove all the bad resolution images and so on. For localization, we need to translate the labels and align all the units into meter. That's the unit we're using. Normalization, we need to have the same coordinate system, same layer structures, maybe snap all the wall to 90 or 45 degrees when appropriate. Deduplication, that we remove all the duplicate data from our data set. And finally, we run human validation loops at the end. So once clean, our data set is there, we need to translate every single plan into a graph so that our neural network model can work with it. why graphs? In our model, what we did, rooms are nodes, and door, walls, and the functional relationship are presented as edges. So the convolution on images blurred the semantics, but graph convolution respects them, and that was key for us. So we wanted to go with neighbor sampling so that the graphs are sparse and GPU friendly, so that we can train it on GPU clusters. And then we used also the node attention so that the model can listen. For example, a corridor shape when deciding the bedroom location, or to add more for a distant, maybe bathroom or something like that. So how do we abstract our units into a graph? In this example, we have three. We have the flats, which is distilled into 5 nodes. The corridor or the entrance, which was node number 4. And the rest of the spaces, bathroom, living room, kitchen, are around the space. And the edges are actually the relationship between the different spaces. And we even distinguish between 2 types of physical connection or connection, so physical and functional. So think of physical connection as doors that you can walk through. So corridor to kitchen, corridor to living room, and so on. In functional connections, for example, a bedroom that should be close to a bathroom, but they don't have an actual physical connection, a door. So it's just a proximity. And this dual edge type schema makes our circulation and program separated in the set. Scaling up, we can go to dozens of rooms, and that just you get 100 edges. However, the inference time stays near linear because the neighbor sampling caps the fan out per node. As for the synthetic data, most of the data is labeled and ready to use. As we can see here. So we just get an original image, room, and then we can build a graph straight away. However, it is critical here to look at licensing because not all the data is available for commercial use. The data you see here on the screen, for instance, was only published for research purposes. So you can use them for in academia, you can use them for non-commercial use. But for us, it was not really usable. So we have, of course, you can always acquire the license for the data, but it was tricky for us to differentiate between what is actually fair use and what is explicitly forbidden from us to train on. On CAD data, what we did, we built our pipeline using the Autodesk Web Services. So we collected all our data in one bucket. We converted everything into DWG and DXF files. We tried to go as much as we can with DXF, but the file that we had with DWG, we kept them like that. That we were pushed into one bucket and converted to SVF2 files. And then we had 2 platforms kind of based on the viewer API, where we could check for the features that we wanted and extract them. And in case of incoherence, we could always edit the file manually and send them back into the loop. And if any overlay were detected, and then we go back again until we satisfy the final human inspection. For the BIM data, it had pretty much a similar pipeline, except that we worked here with Revit and IFC files. And it was really easier for us to extract the room and spaces and labels. So it was there, we just had to fetch it. Of course, always we had the human inspection phase, and we developed a specific C# Revit plugin that extracts the data, where we could test our pipeline locally on few files and specifically on the edge case files before we go and we run it on all our data sets on the Autodesk Web Services Cloud. As for raster, so raster is it's pretty much images. So think of PNG, JPEG images that you could find on the internet. And we needed to have a workflow where we can extract the features. So what we did, we tried a little bit with different segmentation models. Here on the screen, you see the result from Segment Anything model, which is a popular segmentation model by Meta. And to our surprise, actually, when we played with the different models with the parameter count, we expected that edge detection and contouring would give us better results. But in our cases, with edge detection and contouring off, we were able to extract the feature. And I think the reason for that is that most of our floor plan were black and white, and the one who were colored, we just applied the grayscale filter so that they are just black and white pretty much. And that helps the model to extract the spaces. And then all what we need is just to cluster them and then get them combined with the labels that we got. So we had another layer that extracted the labels, translate them to English, and we combined both data. And we were able to generate our graphs from the raster images. However, not all the graphs, of course, were valid. We got a lot of invalid graphs. On the left side, you see a correct graph representation where we have the actual representation of the room connections from the dataset. On the right side, you see an example of an incorrect graph that we had, which at a first look very similar, but it contained errors due to incorrect connections, maybe shifted connection, duplicated. In some data set, they had multiple spaces labeled similarly, so the algorithm failed. And we had to sort that out manually. Overall, we end up with 32,000 residential graph representation that are ready for training from our original 47,000. And here we can see a little bit the distribution of the loss over our preparation set. So from 47,000, we went to 32,000. A lot of the loss was on the raster side. So we went just to about 3/3. The reason for that is, as you expect, a lot of the raster dataset we had with low quality and maybe low resolution. And we were not able to extract a lot of usable features from the images. BIM and CAD, we had the results that we expected. And in synthetic, to our surprise, it was a lot of the data in the dataset that we collected that we were able to use commercially was duplicated. So we had to cut that quite a loss. So overall, it was 32,000 valid graphs that were used in this particular iteration. We're always trying to collect more data to improve the accuracy of our model. To sum it up, I believe that data preparation is the real hidden cost of AI. And it's even harder in the AEC field because it's really hard to get proper labeled data that you can use. So on our side, we absorbed it so that you don't have to do it. Let's just automate this thing together. You can always reach out to me at ayub@d3companion.com. We're open to talk, and thank you for your attention.